So I've talked a little bit about primitive types and references and the differences between them. References are the kind of variable you use to hold on to an object and do things with it. Primitive types are types that are built right into Java. They're core to the language. You don't need to create an object to store a primitive type. You can store it in a local variable, and they're usually very simple. So let's go through a list of them so you'll know what they are. There are 4 different integer types, and they go in order from smallest to largest: byte, short, int, long. So for instance, a byte is an 8-bit integer, and it can take on a range from -128 to 127. And if you're wondering if that's really 8 bits, 1 bit is used for the sign, positive or negative, and the remaining 7 bits are used to store the number, more or less. Exactly how that's done, you'll learn in 61C. We're not actually going to talk about how integers are represented in your computer's memory. In 61B, you'll learn that in 61C. Then we want to move up to larger numbers, because not everything you want to store is in the range from -128 to 127. So if you're willing to spend a little more memory, then you can get a 16-bit integer called a short, which gives you the range from -32,768 to 32,767. You can use an int, which a lot of people tend to use by habit. And these are 32 bits. And so that gives you a range basically from about -2 billion to +2 billion. And finally, there are longs. Which are 64-bit integers, and I'm not going to write out the range, but they go from about -9 quintillion up to about 9 quintillion. And you know, when you're writing code, you can't really go wrong by comparing just about everything along, except in the special case where you need to save memory and you're storing a lot of numbers. So if you're storing just a huge number of numbers, you might want to make them something smaller than a long. But for everyday use of ordinary numbers, the safest thing to do is declare most of your integer numbers to be longs so that you don't accidentally overflow by trying to store a number that's too big to fit in memory. Then we have the floating point types, which include the double precision floating point, which is a 64-bit floating point number. And generally, these are used for anything with a decimal point, like, say, 18.355. And again, when you take 61C, you'll learn how floating point numbers are stored in memory. We're not going to touch that here. It's kind of complicated. Sometimes, if you're really pressed for memory, you might want to use big arrays of floats instead of big arrays of doubles. Floats have only half the accuracy, so you're throwing away decimal points, you're throwing away precision, but they only take 32 bits to store each one. A couple of other primitive types that Java has are not numbers, or not exactly numbers. There is a Boolean type, which can only take on 2 values. It's either true or it's false. And the words true and false are actually built-in Java keywords. So you can write a line of code that says B equals false. And finally, we have a primitive type specifically for storing characters like you would type on a keyboard. often pronounced char. In Java, chars are 2 bytes long. They're 16 bits, and they're not signed. You can kind of treat them as numbers if you want to, and in that case, they're never negative. They're always positive or 0. There are a few conventions for when you want to use numbers, what you need to do. One of them is that if you just write a number in a Java program like 12, Java is going to assume that that's an int unless you tell it otherwise. So if you want a long number, you actually have to add a little L as a prefix. So in Java, you write 43L as a way of saying, I want the number 3, but I want it expressed in 64 bits, not 32 bits. You don't actually need that L in this particular line of code, but the reason you don't need it is because 43 is a really short number. If you leave that L out, Java will create a 32-bit long 43, and then it will see that you're trying to assign it into a long variable, and it will pad it out by adding 32 extra 0 bits in front of that number so that it fits in a long. But if you weren't storing 43, if you were actually storing a really long number that's bigger than 2 billion, or it's too big to fit in an int, then you actually have to write that L. And another convention that Java inherits from C is that when you write a double and floating point value, meaning an actual number, not a variable, then to let Java know that it's a float, it must have a decimal point. So for instance, you might write double y equals 18.0, just to make it totally obvious that this is a floating point number. The Java compiler doesn't require this 0, but it does require this decimal point. I usually write the 0 in as a convention so that it's easier for humans to spot the decimal point. And if you want to assign a float value, then you need to write an F at the end of it. So for instance, I want to write out the number 43.9, but I want to store this in 32 bits, not 64. Well, I write an F at the end, and that tells the Java compiler this is a 32-bit version of that number. Any questions about any of this? Yeah. What's the point of the F? Well, if I just write 43.9 here without the F, Java's going to say that is a double precision 43.9, and it's going to express it in 64 bits. Then when you try to take that 64-bit number and store it in a 32-bit variable, the compiler is going to say, no, you can't do that, because you might lose precision or overflow the number when you do that. So your alternative to this is you'd have to use a cast, which is something I'll talk about in a minute. Yes, Berkeley shirt? Louder, please. The L and F are not case sensitive, no. Upper or lower case doesn't matter. Question? So it's not like a string. Characters really are expressed differently in Java as well. So a character value, did I write this down? I guess it's coming later. But the way you do a character is by putting it in single quotes. And by the way, this is always actually the right quote or apostrophe that's used here. And so essentially when you use char, you're more or less restricted to using values of this, like this, which are basically one character inside quotes. There are other ways to specify characters as well, but yes?
When compiling programs, when I would just write double y is equal to 18 and it never give me any issue. Does the Java compiler perform some sort of implicit casting?
So you've done something like float f equals 18 and it worked fine?
Yeah.
Okay. I don't know why. I'd have to look that up.
Is that something with newer versions?
That may be. I'd have to look that up too. So, don't know off the top of my head. Java has lots of very complicated rules for when it converts one type to another, and I don't know all of them because there's so many of them. So we have two different types. There's object types, or references, and there's primitive types. And I want to talk about some of the differences between these two, starting with what's inside them. Well, object types always store a reference to an object, or the reference null. Primitive types always just store a basic value. Primitive types can never store a reference. How do we define these types? Object types we define with class definitions. We learned how to do those on Monday. Primitive types are built right into Java. And like it or not, you can't make new ones. So, just the 8 I've told you about. How are they created? How are these values created in the first place? Well, object types are always created with the new keyword somewhere in your program, and followed by a constructor. Primitive types, you can just sort of write them down, and the compiler turns them into values for you. How are they initialized? Well, object types, the constructor initializes them. Primitive types are usually given some default value, which is usually some version of 0. If the type is char, there is a 0 character, and if the type is Boolean, then false is essentially the Boolean version of 0. And how are these things used? Well, we call methods on objects, and that's our most common way of dealing with an object, though not the only way. Primitive types, we usually have operators that transform them from one thing to another, like addition and multiplication, and lots of other ones, which I'll try to go through all the more important operators next. In particular, there are the operators on the integer types, int, long, short, and byte. Include, you can negate a number, you can add two numbers together, you can subtract one number from another, you can multiply two numbers using asterisk as our multiplication symbol, and you can divide two numbers. A more unusual operation that integers also have is the remainder operator. And so the remainder operator is connected to the division operator in the following way. With integers, the division operator always rounds down, or rounds towards 0, I should say. So if y does not divide x evenly, the result is always rounded closer to 0, so you get an integer. Or another way to think of this is that it drops the remainder when it's doing the division. So if you remember how you did long division in school, you just do the division until you're left with some remainder that's smaller than the number y, and you stop there. The percent operator gives you that remainder. And that works for integers only. So 5 of these operators you can do on floating point numbers, floats and doubles. The percent operator is only defined on integer types. And it gives you the remainder. Now, those of you who've programmed in C or C++ are used to thinking of this percent sign as the modulo operator. Remainder and modulo are similar, but they're not exactly the same, especially when x or y is negative, you get different results. So what you're used to the percent sign doing in C, it does not do exactly the same thing in Java. It does something slightly different. So you have to watch out for that. Mm-hmm.
Quite understand the distinction you made between created and initialized. Could you explain that?
Created is when you bring one of these things into existence in the first place, like create the piece of memory that's going to store either the primitive type or the reference type. How does that piece of memory get initialized when it's first created? How there's the difference between how does it get created, what do we do that causes that thing to come into being in the first place, versus how do we decide what gets stored in that piece of memory. So that's the difference between how created and how initialized. Mm-hmm.
I had a question about wrapper classes and how they would fit into which one of the categories. If they're more
What kind of classes?
wrapper classes
Wrapper classes. I'm not sure what you mean by a wrapper class.
or like integer class.
Oh, that's a whole other topic. I'd be happy to talk to you about that afterwards, but that's too big an aside. It's not something I have time to talk about today. Yeah.
Is there no built-in x to the power of y operator?
So there is no built-in x to the power of y operator in Java. There is a math library that has a power operator, but it's not built in. It's a library. Mm-hmm. And it's in the math class, by the way. And I should say a few words about what is in the library. So there is a library called java.lang, which is the library that every program you write, every Java program, automatically imports this library without you having to specify it explicitly. And in that library, you have lots of interesting operations. Most of them are in the math class. So, for instance, there is an absolute value operation. And there's a square root operation. There's a sign operation. All of the things you would expect when you're doing interesting math are in there. There's a few other things that you might find really useful sometime in a few of the other classes. one thing that comes up really often is that you read a number from the keyboard, like someone types in some digits at the keyboard, but you get that as a string. You don't get that as a number. You need to convert that string to a number. Well, there are classes that match each of the primitive types that have methods you can use, like the parseInt method in the integer class will take a string and convert it to a number of type int. So this is how you convert a string version of a number into an internal version of the number. And so likewise, for every primitive type, there's a corresponding class that will do that. Now, one of the more, yeah? An API, the question is, what's the difference between a Java library and an API? An API is just a description of all the methods that are in the library that you can call. So API is the part of the library that is exposed to the user, so you know how to use it. Uh-huh. Can you say that louder, please? Why didn't we define the variable? I'm assuming that it's already defined. Well, that depends on whether or not you already wrote int x. I'm assuming that we did write int x somewhere previously in this program. So Java has rules for converting between different types. And one of those rules is that Java will allow you to straightforwardly assign integers to integers of longer types. But if you want to do the opposite, assign a value to a variable of a shorter type, Java wants you to promise it that you know what you're doing, because you might be throwing bits away. So to demonstrate that, if I have an int and I have a long, well, even though 43, Java interprets that as an int, you can store it to a long because a long is 64 bits, and therefore there's enough room to store a 32-bit number without changing it. And likewise, if you try to directly take the variable I, that's 32 bits long, and store it in L, then that works just fine, because L is 64 bits long and has room to store the whole int. But if you try to do it the other way around, you get a compiler error. And the reason is that L is 64 bits long. It doesn't fit in a 32-bit variable. Nevertheless, maybe you know when you're writing your program that whatever number is stored there is always going to be 32 bits or less. And so or maybe you're willing to throw away the high order bits because you don't need them for some reason. And so you want to go ahead and force Java to take that 64-bit integer and assign it to that 32-bit variable, even though it's going to throw half the bits away. You can do that. And the way you do that is you use something called a cast. So if I write I equals, and then inside parentheses, int, and then L, that's my call to cast. And that's basically your way of saying to Java, I know what I'm doing, go ahead and let me store this big number in that small space, and if I lose bits because of that, I'm willing to handle the consequences of that. And so if you make Java that promise, then Java will let you do that. So why won't Java just let you store a long integer into a short space? Well, Java is trying to save you, just like Jesus. But Java is much more efficient than Jesus. Java will show you the error of your ways today. Today is the day of reckoning. Because you see, what can go wrong is that if L is a really big number that doesn't fit in an integer, then you throw away the high order bits, and that can make for a really hard to find bug. And so that's what Java is trying to save you from, and Jesus is trying to save you from hellfire. Similarly, if you want to go between float and double, if you take a floating point value and assign it to a double variable, that's fine. If you want to do it the other way around, take a double value and assign it to a floating point variable, then you might be throwing away bits, and Java wants you to tell it that you're willing to accept the consequences of that by writing out a cast. And if you don't write the cast, Java's compiler error message is a way of saying, maybe you're making a mistake, think about it. Any questions about that before I go on? In the back? Well, so first of all, the square roots function in the math library takes doubles and returns doubles. It doesn't run on integers, it runs on floating point numbers. So if you wanted to do that, you can take your integer, you can cast it into a double, you can pass it into the square roots method in the math library, and then what you get out of that is going to be another double. If you want to store a double into an int, then I believe, again, you have to use a cast, yes. You have to cast it back to int or back to long, because there are doubles that don't fit in a long. Yes? Will Java divide by? If you say divide int by float, Java will take the int and change it to a float, and then it will divide float by float, and then you get the float result. Mm-hmm. Can you speak louder, please? Why don't I do long L? Up top? Are you talking about this line of code here? Yeah. So here is an example where we're taking something that's short, because Java, when it sees the number 43, Java makes that an int, and then we're trying to assign it into a long variable that has 64 bits. So there's plenty of room to store that int exactly. So it's exactly the same as when I wrote L equals I. It's storing something short in a long space, and so it's happy with that, because nothing can go wrong. Yes? Can you give me an example of what you're talking about? Mm-hmm. Right. The time when you need to do that is when you have a number so big that it won't fit in an int. Because then, if you just write, 4 quadrillion out as a number, Java doesn't like that because it's too long to fit in an int. Yes?
What would happen is say you would use the cost thing for the L, and I'll have the value of 7 billion.
Mm-hmm.
Change it to store it in an int variable. But since you said earlier that int variable is up to 2 billion,
Right.
how would we save?
So I can't give you a complete answer to that because you have to take 61C. The question is, what if L is 7 billion? 7 billion does not fit in an int. What happens? What happens is that your computer expresses 7 billion in binary. That takes more than 32 bits. The high order bits get thrown away, and you wind up with a much smaller number stored in I. Mm-hmm. Say again? You can compare L and I, yeah. If you compare two numbers of two different precisions, Java just promotes the smaller one so it's the same size as the bigger one, and then compares them as if they were the same type. I'm going to move on now to talking about Boolean values and Boolean operations. We're going to be using those a lot. Remember what I said before. There are two values, true or false. Every Boolean has one of those values. It takes 1 bit to store that, and true and false are both Java keywords. You can actually type them in a program. We'll see lots of examples of that. Before I do, though, I want to talk about the most important math operators that you do with Booleans, which are the logical AND, the logical OR, and the logical NOT. So, to do a logical AND in Java, you write ampersand, ampersand. That's the AND operator. To do a logical OR, you write 2 vertical bars in a row. And the exclamation mark is our logical NOT operator. And so it would take a long time to write false or true for every one of these, so I'm going to abbreviate them. But note that in your Java program, you can't abbreviate them. You have to write false or true out in full. So there's 4 different possible combinations of inputs that A and B could be. Some combinations of falses and trues. And A and B is true only if both A is true and B is true. Otherwise, it's false. A or B is true if either A is true or B is true. And it's only false if both A and B are false. And the logical NOT operator, the exclamation mark, just reverses the value false to true or true to false. What's more interesting as operators, though, are the operators that actually create Boolean values. Anytime you do a comparison in Java, when you compare two numbers, for instance, you're implicitly creating a Boolean value. So, Booleans, again, are created always, whether you know it or not, every time you use a comparison operator. And so, you have what you would expect, for the most part. So operators that mean, so when you want to compare two numbers to see if they're the same, you use a double equal sign, which is one of the in my opinion, major flaws of Java that's inherited from C is I wish C had used the single equal sign for comparison, but they don't. You need a double for equality. And it's a very common error when you're starting out programming Java or C that you forget and you use a single equal sign. Java usually gives you a helpful compiler error. C usually just lets you shoot yourself in the foot by actually doing something, some weird computation with that. You can also compare whether a number is less than another, greater than another, less than or equal to another, greater than or equal to another. And when you want to write not equal, we have this wonderful notation, not is an exclamation mark, equal, which is what we do because our keyboard doesn't have this symbol. Question? Python's what? Is. I don't know. I actually don't use Python, so I don't know what the is keyword does in Python. Anyone know?
Is for identity. It checks to see whether two objects are the same.
Oh, checking whether two objects are the same. Yes. In Java, it's a method called dot equals, and we'll cover that in a later class. Mm-hmm. What are the false values? Well, null, zero, false are all kind of analogous to each other. But Java is not like C. In C, you can use the number 0 as if it were false. Java does not let you mix 0 with false. Java is strict about that. Booleans, ints, they're not the same thing. So you can't do the C trick of taking some number and putting an if in front of it. Let me give a few examples of these. So I can declare a Boolean, x, and set it equal to the answer to the question, is 3 equal to 5? And of course, 3 is not equal to 5, so after I execute that line of code, x is now false. I can go on to ask the question whether 4.5 is greater than or equal to 4.5. And of course, yes, 4.5 is greater than or equal to 4.5. So now x is true. I can put expressions in. So I can ask, for instance, is 4 not equal to 5 minus 1? So I can throw in mathematical operators before I do my comparison. And I can even compare Booleans with each other. So I can ask the question, is false equal to the answer to whether or not 3 is equal to 0? And 3 equal to 0, that's false. False equal to false, that's true. Yeah. If you remove the parentheses here, it will try to do false equal 3 first, and that will give you a compiler error. Yes. Mm-hmm. Are and or what? Yes, they are short-circuited. I'm not going to talk about this now because I don't have time, but this will be in discussion section. Your TAs will discuss short-circuiting in discussion section. So the reason why we want conditionals usually, the reason why we want Booleans usually is so that we can use them in conditional statements like if statements. So let's learn about if statements. You probably know what an if statement is. It uses a Boolean expression to decide whether or not to execute a piece of code. So we say if some Boolean value is true, then we should execute some statements, which I'm going to always put in brackets, because that's the style I like. So, again, Bool value can be an expression inside those parentheses, but it has to be an expression that simplifies down to a Boolean in the end. The fact that you require, well, let me rephrase that. The parentheses around the Boolean value are required. And why are they required? I don't know. It was a bad decision made in C that Java inherited. And I like to, again, always maintain my convention that you use braces around your statements, because I think that's better for when you're modifying code. But it's possible to leave out the braces and just have one statement that's conditional. So the statements in there will only get run if bool value is true. If bool value is false, they don't run. So let's use this to do something. I'm going to draw this out a bit by using a Boolean variable, even though we don't really need it. What this line of code does is it takes your score in 61B, which is a number from 0 to 200, and if that number is greater than or equal to 75, or is it 85? Wow. Well, anyway, if it's greater than or equal to 75, you pass the class. You can also have what's called an else clause after your if clause is over. And the else clause gives you some instructions that you're going to execute only if the Boolean is false. So in other words, if we reach this point, that means that your score is less than 75. That won't happen to any of you, of course. To get more interesting effects out of these, you can do several things. You can nest an if clause inside another if clause, and you can daisy chain if-else clauses together so that you can choose between lots of different possibilities instead of a few. And to show you an example that demonstrates both of these things, let's write code that finds the maximum of 3 different numbers. So here's my logic. First, I'm going to compare 2 of the numbers, column x and y. If x is bigger, then I know y is not the maximum, so let's compare x to z. If x is bigger than both y and z, then the maximum is x. If x is bigger than y but not bigger than z, then the maximum is z. All right, so we've completed the first conditional. We know everything that's going to happen if x is greater than y. If x is not greater than y, then the next thing we do is we compare whether y is greater than z. Because now we know that x is not the maximum. It must be either y or z. And if y is greater than z, then y is the maximum. Otherwise, z is the maximum. Any questions about that? Mm-hmm.
Does Java just not have an else if statement, and that's why you have to do it like that? Is there no way to say, if something happens, then you execute this first line, else if you execute else if a boolean, then you execute the next line, et cetera, so you get sort of an else that executes if all the ifs and else ifs fail?
Java does not have an else if statement. Java does have a switch statement, which I'll talk about shortly, which sometimes, but not always, allows you to choose from a whole bunch of different conditionals all at once. So, yes? Daisy chained is the term I use for when I do this. So, I'm just coming out of an else clause, and I immediately do another if to test a second possibility now that I know that the first possibility has failed. Yes?
It was in the last example, but you had the output convention rather than like some print or like return or something. Is that a return value that returns that string? Or?
I just used the word output because writing system.out.println takes too long. That's all. Mm-hmm. Other questions? All right. So let me talk about another alternative, a different way besides the if statement that allows you to choose from more than one option at the same time. It's called the switch statement. And switch is somewhat limited. You don't use arbitrary Booleans. What you do is you take a primitive type and you can compare it to a whole bunch of different values all at once and branch based on which value it has. So for instance, let's suppose that we have an integer called month. And we're supposing here that month is an integer between 1 and 12. 1 is January, 2 is February, 12 is December. And so we want to figure out how many days are in that month. So inside a switch statement, we have a bunch of different cases that refer to different values of month. So for instance, there is the case where month equals 2. That means February, in which case there are 28 days in February. And so I write my code that assigns the number of days, and then I end this particular case with a break statement. The break statement tells Java this case is over, don't execute code from this point on. But then we can write another case. So April has 30 days, but so does June, and so does September, and so does November. So what I'm going to do is I'm going to combine 4 cases into one. These are 4 different months that all have 30 days. And so for all 4 of those cases, I do the same thing. I set the variable days equal to 30, and then I'm going to have a break statement that breaks out of there so that I don't execute any more code after that point for those 4 months. There are 7 months left, and I'm going to put all of those remaining 7 months into one case because they all have 31 days. And so the way I did that is I wrote a default case. The default case is the case that gets chosen if all of the other cases didn't happen. So the month was not February or April or June or September or November. Therefore, we have 31 days. When you write a switch statement, you do not have to have a default. If you want to, have it. If you don't, don't. So again, the break statement jumps to the end of the switch statement. And that means basically after this bracket at the bottom, you continue execution from below that point. So what would happen if you left out this break statement is that in these cases, 4, 6, 9, 11, the code would just keep on going through into the next case and start executing that case as well. Once in a while, that might actually be desirable behavior, although it's usually considered bad style to take advantage of that. Yes? No, there is not a way to do comparisons in a switch statement. You can only compare month or whatever's in that top variable with a bunch of different specified values, which cannot be variables. Technically, you don't need a break at the end of the default. So if I left out this break statement, that wouldn't do anything bad because it's the last case. But there's a good reason to put it there anyway, which is when you write a program, you want to write the program so that it's easy to modify and change. So for instance, if somebody were to add another case after that one, you would want the program to still work correctly. Yeah? If you have a choice between a switch and an if that have the same functionality, usually you judge which one is easier to read. This switch statement, it's not clear if this is better or worse than the corresponding if statement. If every case was different and you had lots of different cases, that would probably be a lot clearer than the corresponding if statement. Yeah? Yeah, you can... Oh, sorry, can you use or inside the case? No, I'm sorry, you can't, no. The cases have to just be primitive values. And so you're pretty restricted in what you can do there. Yeah? No, default doesn't have to be the last case. I think the order of the cases doesn't matter. So I want to talk about return next. Return has something in common with conditionals, which is that it affects the flow of control through a program. Specifically, it causes a method to end when it's executed, and the method ends immediately. So when you execute return, the method ends, and the method that originally called that method gets control back and continues executing. So to give an interesting example of why you might want to return before the end of a method, here is a recursive program that prints all the numbers from 1 to x. This is obviously not the most efficient way to print the numbers 1 to x, but it gives you a sense of how more interesting recursive stuff could be done. So this recursive method, 1 to x, takes in a number x, and if x is less than 1, then there's nothing to print, so you just return. Otherwise, it calls itself recursively to print all the numbers from 1 to x minus 1. We're counting on the fact that this is the base case that will stop the recursion. And after printing all the numbers from 1 to x minus 1, then we print x. The return keyword serves a dual purpose. It's also the way by which a function returns a value. And let me tell you what I mean by the word function in Java. In Java, a function is just a method that's declared to return a type other than void. So, for instance, let's go back to that code we looked at for figuring out how many days there are in a month. So, right here. What I'm going to do is I'm going to package this code up in a method. And instead of assigning 28 to some variable days, I'm just going to return 28. So when you have a return statement there, you don't need a break statement, because the return statement already changes the flow so that you leave the method and you don't never finish the switch statement. And so this way you can break out of the switch statement by returning instead of breaking. And that breaks you not only out of the switch statement, but out of the whole method. And I also want to point out that the return value can return an expression, not just a value. So you can write something like return x plus y minus z if you want. Any questions about return? Mm-hmm. Yes. So if in that case you're returning a Boolean type. If you write return days equals 30, then your return type has to be declared to be Boolean. But you can do that. Or did you mean a single equal or a double equal? Okay, yeah. What I said then. Mm-hmm. If you use break, you can't use break to return a value. In the recursion? Yeah. In that, there you could have used, there you could have used break, I think. No, you can't. I'm sorry, no. There's nothing to break out of there. Yeah, actually, if you use the word break instead of return there, it won't do anything. There's nothing to break out of. I don't even know if the compiler will let you compile it because there's nothing to break out of. There's no switch statement, there's no loop, so. And speaking of loops, that's our next topic. So it's hard to do anything interesting in programming unless you have conditionals and loops. So we're going to get both of those out of the way today. A while loop, well, a while statement is very much like an if statement in Java. They're written in almost the same way. The difference is that the while statement will keep executing the same code over and over again as long as the condition is true. Whereas an if statement executes it at most once. So to show you an if statement, I'm going to write a little program that figures out whether or not a number is prime. So here's my method isPrime. It takes in an int n. We want to decide whether n is prime and return a Boolean, true if it's prime, false if it's not prime. So what we're going to do is we're going to test it against every possible divisor from 2 up to n minus 1. So we have some divisor, it's initially 2. And we're going to keep increasing the divisor until the divisor is equal to n, and then we stop. But as long as the divisor is less than n, we're going to check whether or not n is divisible by that divisor. So you'll notice I've used the remainder operator here to figure out whether or not my number n is divisible by the test divisor, apparently divisor. And if the remainder operation, if the remainder you get when you divide n by divisor is 0, that tells you that n is divisible by divisor, and therefore n is not prime. In which case we immediately return false. There's no need to keep looping and testing other divisors once you find one. But if it's not divisible by divisor, then we're going to increment divisor, make it 1 larger. So remember, that's the same as saying divisor equals divisor plus 1. And then we're going to try again with a bigger divisor and see if n is divisible by that number. And once the while loop is done, once it's tried every possible divisor and failed, then and only then do we know that the number is prime, and we can return true. So we've tried every divisor, none of them divide n. Now we know it's prime. So let's come back to the while loop. When execution first reaches the while loop for the first time, it sees that test, divisor less than n, and it tests whether or not that's true. So that test, divisor less than n, that is known as the loop condition. One thing a while statement shares with an if statement is that if the loop condition is false the first time you get to it, you don't execute the loop even once. There's no rule that says the loop body has to be executed at all. It's only executed the first time if that condition is true. But if the condition is true, then we go ahead and we execute everything inside these braces. And so this stuff here is called the loop body. Inside braces. So if the loop condition is true, we go ahead and we execute the loop body. And when we get to the end of the loop body, we go and we test the condition again. And if the condition is still true, we jump back and do the loop body again. And then we test it again, and we keep looping until the loop condition is false. One word that will come up a lot is an iteration of a loop. So an iteration is one pass through the loop body. And so if this method goes all the way to the end, it does n minus 2 iterations. And again, if the value we start with is 2 or less, then that means the while statement is going to be false the first time we test it. And so the loop body won't iterate even once. Questions about that? Yeah. Yeah, if the loop body does not iterate, then it jumps right to whatever is after the closing brace, which means this line return true. Yes. There's another kind of loop. Well, there's a couple of other kind of loops besides while loops. Another one is called a for loop. A for loop is basically a shorthand way of writing certain kinds of while loops that people would write all the time. And so what I'll do is I'll show you what a for loop means by showing you how it gets transformed into an equivalent while loop. So in a for loop, you write for open parenthesis, 3 different things inside these parentheses. First, you put some sort of initialization, which usually initializes a variable that you're going to use for the loop condition. Then you put the loop condition, and then you put a sort of next expression whose job is to update the loop variable. And then you put whatever statements you want to execute inside the loop. And that is equivalent to the following while loop. A while loop where we do the initialization once. Then we do a while loop on the condition. And then we have the statements inside. And then we finish each loop iteration by doing the next condition from the for loop. So whenever you see a for loop, you can mentally transform it into a while loop that will help you understand exactly what it's doing. So what I'm going to do is I'm going to go back and shorten my primes program here a little bit by using a for loop instead of this while loop. So I'm going to erase the while statement as best I can. And replace it with this for loop. All right, so by putting this for statement there, I can eliminate this initialization, because now the initialization goes inside the for statement. And I can delete as well this increment of divisor, because now I've taken it and I've put it inside the for loop. And so the for loop is handy in a way because it puts together all the information you need to see to understand how many times this loop is going to iterate total and how divisor changes each time you iterate. So this code now with this change does exactly the same thing as the code I had before with the while loop. Yeah. If you what? I'm going to talk about the continue statement later. We're not there yet, but I'll talk about it probably in the next lecture or two. All right, so now what I want to do is show you a common mistake among beginning Java and C programmers. To illustrate this common mistake, I'm going to write a little program that prints all the primes in the range from 2 to n, but the code I'm about to write has an error in it. See if you can spot the error. All right, so I claim this code prints out all the numbers from 2 to n. Where's the error? Yes, sir. It should be less than or equal to n? Yes, correct. So the error is here. And the reason why this is an error is because I want to print out all the numbers from 2 to n, which means I have to iterate over all the numbers from 2 to n. But this loop condition is going to stop us before we do n. We're going to iterate from 2 to n minus 1, but then we're not going to do an iteration when I is equal to n. It's just going to stop right there, and if n is a prime, we'll never find out. So that is wrong, and the correct thing to do is to use the conditional I less than or equal to n, and that makes sure that we include a loop iteration for n and find out whether or not n is prime. All right, so let's suppose we've corrected the code now. It now says I less than or equal to n. When we finish the for loop and this method is about to return, what is the final value of I? Anyone? Actually, no. N plus 1, yes. So when we get to the very end of this method, I will have a value equal to n plus 1, because after we did the loop iteration for I equal to n, we got to the end of the loop, we incremented I one more time, and now I is bigger than n, so that loop condition is no longer true and we stop. So when we exit the loop, I will be equal to n plus 1. Mm-hmm.
Is it
Is it? Yes. I think we did this in the lab, but when you add a string and a number, Java automatically converts the number to a string. All right, we'll talk more about iteration later, but right now I want to have something interesting to iterate on. So let's learn about arrays. An array is an object storing a numbered list of variables. Each variable is itself either a primitive type or a reference. And the variables are always indexed from 0 in increments of 1. So for instance, an array of characters would look like this. Here's an array of 4 characters. And as I said, these characters have indices, and they're indexed from 0. So when you have an array of length 4, its indices are 0, 1, 2, 3. In order to do something with this string, I need to have a reference to the string, because in Java, strings are always objects. So let's make a reference for my character array. And now what I want to do is, I've drawn this picture of an array of characters and a reference pointing to it. I want to write the code now that creates this. So I got to start by having some place to store the reference to the array. And here's how I get that. I declare a variable called C, and the type of C is array of characters. That's written char, open bracket, close bracket. Got to use square brackets. Now, this reference can reference any array of characters. Of any length. So C does not decide how long the array is going to be. C can point to an array of any length, as long as it's an array of characters. Now that I've got that reference, I want to actually create the array of characters. And just like with any object, you create it with the new command. What you put after the new is a little weird, though. You don't put a class name, you put something like this, char4. So this says, please allocate for me a brand new object, which is an array of 4 characters. And so that creates this object and assigns that reference to point to that object. So now that we've got the object and a reference to it, we can start filling in the characters themselves by writing C0 equals B. I'll skip the middle 2. And so this is how you assign values to members of an array. And it's important to know that if you try to assign to an index that isn't actually in the array, that your program will stop and barf, but not at compile time. At compile time, the compiler doesn't know how long the array C is going to be and doesn't try to figure it out. It waits until runtime. So when you're actually running your program and you try to reference index 4 of an array whose indices are 0 through 3, then it barfs. And you get what's called a runtime error. To be precise, the runtime error you get is called an array index out of bounds exception, and that's one word in Java. So a runtime error, again, is an error that doesn't show up when you compile the code. It only shows up when you run the code, and then Java tries to execute something it can't execute and gives you an error message, and your program stops running, and you're very sad. Yes?
Before you assign characters to each of the slots, is it just empty, or what would happen if you were to check that? Like if you, before you assign B to C is 0, if you were to check what C0 is, it would just say blank.
Before you assign characters, whenever you construct an object, including arrays, every field or element in that object gets initialized to some version of 0. And there is a 0 character, in fact, the character whose bits are all 0, ASCII 0, and that's what these will be initialized to, but until you assign something explicitly. Yes? If you're not sure how many characters you are, you have to wait till you find out and then create an array of the length that you need. So arrays, you can't change their size. Once you allocated an array, it's that size forever. If you later discover that it's too small and you need a bigger array, you need to allocate a new array, copy all the stuff from the old array to the new array, and get rid of the old array. Yeah. Oh, go ahead, please.
Is there a way to do the BLUE all in one step, or do we have to go C0?
There is a way to do the BLUE all in one step, but I'll show it you later. Not today, another day, soon. Mm-hmm. An array of references? Yes, you can create an array that references different types of objects. I'll show you how to do that in a later class. Yeah. A single character string is completely different from a char. They are not the same animal at all. How do you what? Well, they're different classes for one thing. A string is of class string. A bunch of chars is of either class array of chars. Mm-hmm. Why isn't a char a native type? I don't understand the question.
So why isn't a char like an int? Or
A char is like an int. It's a primitive type.
then why do you need to like take care of like an object?
You only need an object if you want an array of them, if you need more than one in one place. I'm going to move on, sorry, because I don't want to run out of time. When you have C referencing an array, you can look up the length of that array, because every array has a length field that tells you how many elements are in it. So it's a field that every array has called length. So if your array reference is C, then you look at C.length. You can never change this field. Because if you try, you'll get a compile time error. But if someone hands you a string and you want to know how long it is, that's how you find out. You look at that field. So I want to use arrays now to do some useful work. We're going to come back to the problem of how to figure out all the primes from 2 to n quickly. And the algorithm I showed you for doing that, it works, but it's really slow. For each prime, you have to go through all the possible divisors and make sure that none of them divide the prime. That actually comes out to be really slow if you want to find, say, all the prime numbers from 1 to a billion. It's going to be too slow. Here's an algorithm that's actually fast enough that you can figure out the primes from 2 to a billion with a decent computer and a little bit of patience. We are going to use an ancient algorithm called the sieve of Eratosthenes. Eratosthenes was an ancient Greek mathematician and the inventor of geography, apparently, who also invented this algorithm. The idea of the algorithm is that all of the integers are assumed prime until proven composite. Composite is the opposite of prime. It means it's composed of prime factors. And for each prime factor, for each possible prime factor, we're going to go through all the larger numbers and eliminate the ones that are multiples of that prime factor. In other words, we're going to mark every non-prime we're going to mark as non-prime every integer that's divisible by a given divisor. So let's get started on this method. So the first thing this algorithm does is it allocates an array of booleans, one for each number that I want to test. You'll notice that this is an array of n plus 1 booleans. That's because I want to have a boolean with index n. If I allocate an array of n booleans, they only go up to n minus 1. I want them to go up to n. I'm going to, again, go with the policy that all integers are assumed prime until proven composite. So I'm going to go through this array with a loop. And set every entry in the prime array to true from 2 to n. So again, our policy is every number is prime until proven composite. So from here, what we're going to do next is we're going to iterate through all of the possible prime divisors from 2 up to the square root of n. And we're going to use the prime array to know which of the small numbers are prime when we're canceling out large numbers and finding large numbers that are not prime. So again, we're going to go through each possible divisor. Up to and including the square root of n. And for each one, the first thing we're going to do is we're going to check if it's prime. And the reason why is to figure out which numbers are prime, we don't have to test a number against every possible divisor. We only have to test it against the prime divisors. So if a divisor is prime, what we're going to do is we're going to mark all the multiples of that divisor as not prime. So we have a loop that goes through all of the multiples of divisor, starting with 2 times divisor. And going up to n. And for each multiple of a prime divisor, we're going to mark that multiple as not being prime. And so that's the code. Well, that's most of the code. We still have to print out the primes. But what this loop does is, again, we go through all possible divisors, we check if a divisor is prime. If so, we go through all of its multiples and mark them as not prime. So eventually we find all the numbers that are not prime when we hit one of its divisors. Question? Okay. A question you might want to ponder today after you go home is, why is it that we only need to check the divisors up to the square root of n? Once we've done this, we're going to print every number from 2 to n that hasn't been marked not prime. This part's pretty simple. Go through all the numbers, check which ones are prime, print them out. And that is our complete method for printing all the primes. One minor thing I want to point out is that the elements 0 and 1 are never used at all. We never look at them. We never even initialize them. Because they don't matter. They're not divisors, and we know that, and they're not considered primes, so we don't care about them. And so, there's like 2 bits of memory that are wasted storing Booleans for those numbers that we're never going to use, but that doesn't matter. It's too small to care about. Questions about this? Mm-hmm.
Why can't you add space to I since I is a string and space is
Why can you do...
add space and I together in a string?
when you add a space plus I, Java converts I to a string and then concatenates the 2 strings together. And it does it for you automatically for convenience. Mm-hmm. Not everything in Java is immutable, just strings. Most objects in Java are not immutable. Strings are kind of an exception. This is very mutable, yes. Arrays, you can change them all you want. Mm-hmm. Mm-hmm.
For the part with the nested for loop, what if we use the variable I twice in both orders? Anything that happens?
For the nested for loop, what about using I twice?
Like what if we use I in both for loops?
I don't see... you do need to keep track of what divisor you're using when you do I, so I do need another variable, yes. Yeah, I don't know how to do that with just one variable. I want to talk about multidimensional arrays. So a two-dimensional array is an array of references to arrays. A 3D array is an array of arrays of arrays. A 4D array is an array of arrays of arrays of arrays, and so on. So to do an example, and to make it interesting, I'm going to do a non-square array, because Java lets you do that. I'm going to do Pascal's triangle. So what is Pascal's triangle? Maybe some of you have seen it before in recreational mathematics. The idea is that you start with a few rows that look like this. So row 0 is just the number 1, and row 1 is 2 ones in a row. As you go down the pyramid, you're going to have a triangle that gets bigger and bigger as you go down. You're always going to have ones on the leftmost column and the rightmost column. Between those columns, you assign numbers by adding the two numbers above them immediately to the left and the right. So the reason there's a 2 here is because 1 plus 1 equals 2. The next row, I'll have 1s on the outside. I'll add 1 plus 2 to get 3. I'll add 2 plus 1 to get 3. The next row, I'll have 1s on the outside. I'll add 1 plus 3 to get 4. I'll add 3 plus 3 to get 6. 3 plus 1 to get 4. And so on. So here's row 5, just so that we've got enough for some intellectual usefulness. Now, Pascal's triangle has an application to understanding polynomials, specifically the coefficients of polynomials. For instance, row I of this pyramid represents the coefficients of this polynomial, x plus 1 raised to the power of I. And let me give you an example of that, just to make that concrete. If you take x plus 1 to the 4th power, you get x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. And the coefficients of this polynomial are exactly the numbers right here in row 4 of Pascal's triangle. 1, 4, 6, 4, 1. So let's look at a little code that creates Pascal's triangle for us. And to save a little time, I've just written the code out here. So this code, it works with two-dimensional arrays, and in fact, the return value you can see is Pascal's triangle n is going to return an array of arrays of ints. This will be a two-dimensional array of ints. The very first line of code declares a variable, pt for Pascal's triangle, and that's where I'm going to store our return value, but we need to build it first. To get started, what I'm going to do is I'm going to allocate an array of n arrays of ints. So here's what that looks like. I've got my variable pt here, which is a reference that can reference an array. So let me put an array here. Let's suppose for now that n is 5. So I'm going to allocate an array of length 5. Each entry in this array has space for a reference to an array of ints. I haven't created that array of ints yet. So, we've got this funny notation up here where we wrote int open bracket, n, close bracket, open bracket, close bracket, which tells Java, I want to create the first array of n references to arrays of ints, but I don't want to actually create those arrays of ints themselves yet. I'm going to do that in a loop. So here we've got this loop that loops once for each row of Pascal's triangle. And the first line allocates a new array of ints of the appropriate size. So we're going to allocate an array of length 1 to be the first row of Pascal's triangle. We're going to fill it in with the value 1. We're going to fill it in again with the value 1, just to be sure we put a 1 there. And then we're going to iterate back to the top of the loop. And now we're going to allocate a second row of Pascal's triangle. And we come to this line of code, which puts a 1 in that first spot. We come to the inner for loop, which still does nothing because I is equal to 1, j is equal to 1. Is 1 less than 1? No, so we don't iterate. We just jump ahead to this line of code here, which puts a 1 in the second box. And now we iterate again. We allocate a third row of Pascal's triangle, of length 3 this time. We put a 1 in the left box. Now, for the first time, we're actually going to execute the inner loop. So this for statement here now finally gets its inner loop executed, and that inner loop is the part that sums up these two numbers here together and writes the result into that box. And that's all the inner loop does on that pass. So now we come to this line of code, which writes a 1 again in that right spot. Now we iterate the outer loop yet again. We allocate another array of ints and store it in the array of arrays of ints. We set the left element to 1. We go through the inner loop, which adds 1 plus 2 to get 3, adds 2 plus 1 to get 3. So this time the inner loop iterates twice. And then we come out of the inner loop, we execute the last line of the outer loop body, putting a 1 there. And then we iterate again. I'll do this one more time. So we put a 1 in the left box. The next box is 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and put a 1 in that final box. And that's what our final array object will look like. And you'll notice this is essentially a two-dimensional array, but it's not a rectangular two-dimensional array. It's shaped like a triangle. And so Java lets you do weirdly shaped 2D arrays like that if you want. There's also an easier way to get square rectangular arrays, which I'll talk about probably on Monday. And that's it for today. Thank you.